cosmic storm. Floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light. Riding the waves that are just out of sight.
It's solo time. Time to tackle a particular topic that is difficult to explore as an interview. And I have enough background to go down this rabbit hole. Solo style. Volcanoes and climate. But it's also the last episode of the season. So let's do some cleanup. Season 2 was amazing. Learning the craft, growing as a podcaster, learning search engine optimization, social media, and getting better at science communication. Not to mention building networks and the wonderful guests. I've learned so much from them, and I hope so that you have as well. They're the real stars of the show. It is their work that is presented here. I wanted an outlet when I started this to explore science, learn new things, and have new avenues to view the natural world. To be honest, this process of making whimsical wavelengths is harder than I expected, but at the same time rewarding. Even won an award for Podcast of the Year in the Science category from the American Writing Awards and PopCom conference in Indianapolis as well in Science and Technology. In the many seasons to come, I hope to continue to grow, learn new things, get better at making engaging, deep dive science content. Maybe add a few new tools, and perhaps find new ways to grow the podcast. That process involves you as the listener. We've had one podcast episode that was completely spawned by a suggestion. Perhaps there will be many more. Once there's enough of a community surrounding the show, perhaps an Ask Me Anything episode? I don't know. The point is that the show will continue to evolve. So there will be 3 encore episodes to get through the rest of summer, and come mid-September, Season 3 will start. The current peg or date for that is September 14th. Hopefully I can stick to that as long as real life doesn't get too much in the way, but I'm pretty sure we should be able to make that September 14th to be that seasonal tradition for whimsical wavelengths. Today, though, I wanted to look at one of the many climate myths that is thrown out there by those who don't like data. People who want to believe something is false because it's against their ideology. Well, actually, I'm not entirely sure why people believe this, especially because it can be disproven. In this episode, we'll do just that, and we'll learn a little bit about volcanology and climate along the way. The claim that we are dealing with today, which we know is scientifically false: volcanoes emit more carbon dioxide than humans do. That is a complete and utter false statement. Volcanoes emit way less than what we humans do. Now, where to start with this? I guess I should state a USGS scientist, Dr. Terry Gerlach, detailed this in stark detail in his 2011 paper. And to be frank, this episode follows much of his paper. And we'll probably be returning to his conclusions several times throughout the paper. If not explicitly, but then implicitly. So, let's begin with volcanoes emit gas. And that gas can basically fumigate the area downwind, a caustic mix of gases. The 3 most important volatiles or gases in magma are water, carbon dioxide, and sulfur dioxide, in that order. There are other trace gases like hydrogen fluoride, hydrogen chloride, but they're at much smaller amounts, and we'll leave those aside, as they don't affect the whole calculation of trying to figure out how much carbon dioxide is degassed by volcanoes worldwide. So to look at how we know volcanoes have a smaller footprint or factor when it comes to greenhouse gases than human emissions, we need to understand several things. First, how much carbon dioxide should be in the magma, how much magma is degassed each year, and thirdly, How much do humans emit? So let's start with 1. How much carbon dioxide should be in the magma? Well, how much gas in total? Like the total number of volatiles. The logic goes, if we can estimate the amount of gas in the magma, then all we need to do is figure out how much degasses every year on average, and we'll have a good estimate of the number. There's a lot of nuance in all of this data and numbers, which will hopefully become apparent. A common theme in the volcano episodes here on Whimsical Wavelengths is that magma or lava is not a simple liquid. Today we will bypass the rheology or how magma and lava flows and moves to look more at the chemistry. Because this is not like, say, water from the tap. There are many different chemical constituencies in magma, the biggest of which is sulfur dioxide, taking up just less than half, so 50%, all the way up to 75% of the weight of magma. Gases or volatiles make up somewhere between 1 and 7 weight percent, depending on the environment, and we'll kind of dive into that in just a minute or two. So, how do we know that, you ask? Well, this is the why I wanted to do this episode, to explain how we get to the conclusion. It isn't built in a vacuum or a black box. It's based on a series of real-world discoveries and advancements that were completely unrelated to climate change or climate science. It really was all about the volcanoes. For this first rung of the ladder that gets us towards the final conclusion, let's continue with the geochemistry of the rocks and then melt inclusion geochemistry. So we can get whole rock geochemistry, grinding up the rock into a powder and then running it through an X-ray fluorescent spectrometer. Basically, we hit it with wavelengths. You can think of the result here of what the magma chemistry would be if the rock was melted. For volcanic rocks, would it be the actual magma chemistry? The answer is no. Without getting into the weeds about how magmas change and evolve as they move towards the surface, what is really missing is the volatiles, the gas. Like a pop bottle that you shook, when the magma gets close enough to the surface, it is like the lid is unscrewed and gas is released, because the pressure dropped. The material after an eruption has much less gas in it. It came out of solution and was carried away in the wind. I think I did a pretty good job back at the beginning of this season, Season 2, Episode 1, when discussing Messiah Volcano with this topic. So if you want a deep dive with respect to volcanic behavior, revisit that episode. Unfortunately, magma is much more complicated than a bottle of soda. Soda, we only need to worry about water, pressure, and carbon dioxide. Magma has lots of different chemical constituencies and volatiles, and it changes. As far as volatiles or gas, they'll have different solubilities as well. So that's the ability of a particular substance to stay in solution inside a liquid. Sulfur dioxide, for instance, comes out of solution quite late. If you detect sulfur dioxide, you know magma is close to the surface. Carbon dioxide, on the other hand, is less soluble. Not too long ago, we looked at carbon dioxide flux with Gaetano in episode 18 for Kilauea and its deep magmatic system. And in Kilauea, the carbon dioxide starts to exsolve and come out of solution around 35 kilometers beneath the Earth's surface. And that's deep. For today, and this topic, showing humans are releasing more carbon dioxide than volcanoes, this is a bit of a wrinkle. It's a lot easier to monitor sulfur dioxide degassing. It happens when everything is quite close to the surface, so carbon dioxide will need to dig a little bit more. Remember, I have already divided this episode into 3, and this first part is all about how much carbon dioxide should be in the magma. I actually should have phrased it, how much is in the magma and how much gets degassed. So to get that number, we need a time capsule. We need to find magma before it ever had a chance to pop the top or get out close to the surface and lose its gas. In volcanology, we look for what we call primitive magmas. I've already alluded to this, sort of. As magma travels through the crust and cools and changes, different crystals form and change the concentration of what's left in the melt. Basically, all magma that erupts onto the surface has changed somewhat on its journey. A primitive melt rises quickly from the mantle without significant changes to its chemistry. The reason why these primitive melts are so valuable is we can use them to understand the original chemistries of the magma. And for this topic, we can get close to the original concentrations of carbon dioxide because of melt inclusions. Imagine a crystal, usually olivine, growing deep underground. As it grows, it occasionally traps a tiny droplet of the surrounding liquid magma inside its structure. Because that olivine crystal is incredibly strong, it acts like a microscopic pressure vesicle. It keeps that little drop of magma under the same intense pressure it felt many kilometers or miles below the surface, preventing the volatiles like carbon dioxide from escaping. But even these little time capsules can have a bubble problem. As magma is erupted, it cools. The liquid inside that little time capsule of a crystal shrinks, and a tiny vapor bubble forms. Because carbon dioxide is so unhappy or incompatible or insoluble in the liquid, almost all of it, sometimes up to 90%, comes out of solution into that tiny little bubble. And quite frankly, for a long time, we were underestimating volcanic carbon dioxide that comes from these volcanoes because we were only measuring the carbon dioxide in the glass in the melt inclusion and ignoring the bubble. Today we use Raman spectroscopy, basically hitting that bubble with a laser, wavelengths, to measure the density or concentration of the gas inside. By adding the gas in the bubble back into the gas in the glass, we get a truer original concentration of carbon dioxide. When that magma was entrapped by the olivine crystal, it's important to note that this must still be treated as a minimum, as carbon dioxide could have degassed before it was captured from the melt. One would think that primitive melts, something that can go from the mantle to the Earth's surface relatively quickly, with very little changes, are rare. So, what happens when we can't find good primitive melt inclusions? Well, now we have to use different techniques, like the geochemical buddy system. We look at the ratio of carbon dioxide to elements that behave similarly but don't turn into a gas, like niobium, Nb on the periodic table, or barium. In the mantle, the ratio of carbon dioxide to niobium is fairly consistent and constant. Since niobium doesn't degas when the pressure drops, we can measure the niobium in an erupted rock and use that mantle ratio to calculate exactly how much carbon dioxide should have been there before the eruption started. Okay, we can also do this with hydrogen-3 ratios as well, but we need to really make sure we understand something, because the steps to back out carbon dioxide concentration in magma only really works in your typical basaltic systems. Think mid-ocean ridges like the Atlantic Ridge or the Nazca Ridge, or ocean island basalts like hotspots, so Hawaii, Galapagos Island, Piton-Flonez. And when we apply these methods to primitive basaltic magmas globally, we find mid-ocean ridge basalts come up between 0.05 and 0.25% carbon dioxide. And for hotspots like Hawaii, somewhere between 0.5 and 1.5% weight CO2. It might sound like a lot, but when you do the math on how much magma actually reaches the surface each year, don't worry, we'll get there. But let's go back to subduction zones, because subduction zones are a lot trickier. First, getting primitive melt inclusions are basically never found because the chemistry is so different due to the way melting is caused. In mid-Atlantic ridge or ocean island hotspots like Hawaii, it's primarily due to depressurization. Either as you split the rocks apart, you lower the pressure and you cause melting, or in the case of a hot mantle plume, not only do you have the increase of heat, but you also are moving hot material up towards the surface through the plume and depressurizing and causing some melting. However, for subduction zones, it's the addition of volatiles, namely water. So, a quick refresher, subduction is where one ocean plate is pulled under another. The subducting plate is carrying a lot of water, locked up into the minerals as well as just into sediments and the like. When the plate is plunged beneath the other, it gets pushed into the hot mantle below. It's heated up and put under incredible amounts of pressure, the lithostatic pressure, because of all that weight of the rock above you. This causes the water to be released and rise into the mantle above the subducting plate. Adding water to the hot mantle reduces its melting point and causes it to partially melt. The resulting chemistry from this process is also different. That is an important point. There will be material in the subducting plate or slab that will leave with the water and other volatiles. Why? Because those elements are extremely soluble in the released fluids or volatiles from the slab. One of the knock-on effects of this is increasing the oxidation of the melt. I'll throw out a term here as a bookmark if you want to go further on your own. Oxygen fugacity. The fluids change how the melt behaves and what crystals or minerals are stable. For our story here, we care about titanium oxide, or rutile. It is this mineral that gives niobium a way out of the melt. It can substitute into the crystal structure, meaning we cannot treat it as a geochemical buddy to carbon dioxide like we can for the basaltic systems. It can also add carbon dioxide. See, the subducting slab is carrying more than just water, as we are potentially adding significant carbon dioxide from the slab volatiles. So we need to go back to the slab. As volatiles are expelled, it carries with it large ion lithophile elements like barium and strontium. Well, yes, these are present in the mantle as well. They're only in really quite small quantities in comparison to the slab fluids. The resulting melt here, though, from this process of adding volatiles and melting the mantle is then significantly enriched in these elements. So you can treat the concentration of strontium or barium as a proxy for the slab component of the volatiles. I went back and forth about the best way to explain this. The more simple case is when the mantle melting due to depressurization and heat. Niobium and things like helium-3 ratios work. As described, we can fairly accurately peg the primitive carbon dioxide and check it via melt inclusions. This slab component of adding volatiles and changing chemistry, I think I need a two-step explanation. So I'm going to leave the slab discussion behind for just a moment. Let's look at the volatiles themselves. Active volcanoes are degassing carbon dioxide and others like sulfur. In fact, sulfur stays locked up in the magma until it's quite close to surface. The resulting gases are also easy to detect in volcanic plumes using wavelengths. A little further into this quick aside, similar to what is done in astronomy studying nebula and other planets to observe what gases are present, spectrums, absorption lines. Each gas will absorb different wavelengths, and if we know the original spectra of the light source, we can back calculate what the material was in between. We volcanologists use the same principle. We use a light source, usually the sun, but sometimes we can use a lamp, and we look at parts of the spectrum that are absorbed between whatever we're using to measure and the light source. And typically, we're looking at what spectrums were absorbed by the volcanic plume to back out the concentration of things like sulfur. And then integrate across the whole plume, like say you're driving a car or flying a helicopter underneath the plume looking up into the sun, we can have a total emission per unit time for sulfur. Okay, back on track. Sulfur only degasses after the magma is quite close to surface. We can get measurements from the ground and from satellite-based instruments on the total sulfur emission rates. Now, we can play a game of ratios. Assuming one can find a hot primary fumarole on the volcano, that is. Because that hot primary fumarole, using it, we can get a sample of the volatile breakdown of what's coming through the magma system at the time. We use what is called a Gegenbach bottle. named after Werner Giggenbach, who first introduced them. The bottle essentially has a vacuum in it, using hoses that are shoved into the fumarole. They have to be hoses that are going to withstand that kind of temperature. The valve is opened and the vacuum provides the force to suck up the escaping gas from the fumarole. This gas is sampled carefully to represent what is coming out of the volcano, which can be taken back to a lab and analyzed for its chemical constituents. Now, even here, there are some assumptions, like the hydrothermal system has no interaction. The degassing is linear, tapping only the magma body. And probably a few others that I'm neglecting to mention off the top of my head. There's also other ways of doing this in situ using wavelengths in a similar way to what we've already described, but they have much higher error bars as you're looking above the fumaroles or the vent, and it's all mixing within the atmosphere instead of being concentrated within the fumarole itself. Okay, so we have a ratio of carbon dioxide and sulfur based on this very hot, ideally primitive, it's coming straight from deep within the earth, and because of all that monitoring at the Earth's surface, we have total sulfur. So now we can use a ratio to back out total carbon dioxide. But wait, there's still problems. Sulfur doesn't fully degas from the melt after eruption. Some stays behind and gets locked up in the volcanic glass. So the total sulfur measured via the emissions isn't the total in the magma. There's also other processes that can cause sulfur to be left behind near the bottom of the magma chamber. So the error bars at this point are actually quite large. Yes, we can correct or estimate the amount that stays behind in the glass, in the rock, but those deeper processes are really out of sight, and we don't really have a good way of measuring them and figuring out just how much is being scrubbed out of the system. So let's bring back our large ion lithophile elements. Oh, and melt inclusions too. To overcome these large bars that we have encountered so far requires two things, and some math and trend lines. First, measuring the barium and lanthanum a whole bunch of times across eruptive products. Barium and lanthanum elements, they're non-volatile and stay in the melt until the very end. These ratios are locked in and shouldn't change. And the interesting thing here to note is that barium, as we've talked with strontium above, comes from the slab, and lanthanum does not. It will not increase due to the volatiles. It's coming from the mantle and not the slab. So this means that increasing barium, or increasing the ratio, means increasing the slab component. It's really, really important. We're playing a geochemical sleuthing game here. Now, all we need is melt inclusions. Finding an olivine melt inclusion that we can use for the official sulfur concentration. In arc or subduction settings, this is not easy. Many volcanoes in this setting do not erupt lava with the right chemistry to form olivine. They're too, quote-unquote, evolved, which just means too much change from the primary melt or the first melt produced in the mantle. But in every arc, there are usually a few volcanoes that erupt basalt, and these elusive olivines with melt inclusions can be found. To name drop a bit more, Shoulders of Giants, it was geochemists like Terry Planck and Alessandro Aiupa that plotted the surface gas ratios of carbon dioxide to sulfur dioxide against the whole rock of barium and lanthanum ratios of global volcanoes. They observed a striking, tight, linear correlation. The volcanoes with the strongest slab signature in their rocks constantly had the highest carbon dioxide to sulfur ratios in their gas. The slab components matter. So putting it into practice, this two-step geochemical trick or empirical relationship together. Step 1. We take those rare primitive olivine melt inclusions from the anchor volcanoes, as we'll call them right here, and use them to measure the true deep sulfur concentration of the magmatic source before it hits the surface. Step 2. We pair that deep volatile data with whole rock trace element chemistry, specifically the ratios of barium, which is going to represent the slab, to lanthanum, which represents the mantle. to act as our geochemical slab meters. By plotting many of these values for an arc, trend lines are built. With a robust trend line, we can take the ratio of barium and lanthanum from any volcano or eruption within a particular arc and use the trend line to obtain the carbon dioxide total to sulfur dioxide total ratio. Now we can use the average sulfur still in the glass of erupted products because sulfur doesn't completely degas. So we can get that total sulfur that is being degassed and match it to what we measure on the Earth's surface. And therefore obtain a reasonable value of the carbon dioxide budget for a particular arc. Over the years, this data was collected to understand volcanoes. Primitive melt inclusions, chemical ratios, empirical relationships, they were developed to understand volcanoes and Earth processes, not climate change. That was never the goal. But once you have it, now you can start asking questions because it has a direct application as an input for the atmosphere. It just becomes abundantly clear. And I don't want to get sidetracked into looking at aerosols and sulfate and the expected cooling that happens from explosive volcanism. Perhaps one day I'll walk through a supervolcano and what an eruption would do to climate as a solo episode. The point is volcanoes can have large impacts on climate. We know looking back through geologic time that volcanic activity was one variable changing long-term climate. And obviously in very large eruptions it will have a punctuated short-term climate change as well due to the sulfate. So we have our volatile weight percents. So applying this analysis to mid-ocean ridges and ocean island basalts, like hotspots like Hawaii, we get estimates of our carbon dioxide concentration. And I'm going to be giving it here is grams per kilogram of magma. So at mid-ocean ridges, we have 0.5 to 1.5 grams per kilogram. We can have an extreme high of about 2.5, really, for mid-ocean ridges. For ocean island basalts like Hawaii, we get 5 to 15 grams per kilogram. The extreme side of this is 30 grams per kilogram. And arcs, 5 to 20 grams per kilogram. And the extreme, it can be up as high as 40. Yay, numbers! Well, that is the first part. All done. Now we're on to part 2. How much magma degasses each year? So we have the concentrations. There's 2 different games we can play here. We can calculate an average per year eruptive flux, i.e. how much is on average erupted per year in each geologic environment. Or we can try estimating via measuring sulfur degassing flux and use ratios developed above. Here on the podcast, though, it's easier to talk and walk through the first one. So let's do that and present values for sulfur estimates. For some volcanoes, we have great constraints on eruptive output due to how active they are. The Hawaiian volcanoes, Etna, Masaya volcano, as location examples. When we start to deal with broader arcs like the Cascades or the Andes, there are areas that go thousands of years between eruptions. So detailed mapping of the eruptive products and averaging over the entire arc is the game we need to play. For mid-ocean ridges, spreading rates and averaging the required output for the entire length is what we'll do. So let's take the Cascades as the first example. It has 1 to 2 eruptions per century, which works out to 0.001 to 0.01 kilometers cubed per year for the whole arc. Yeah, there's going to be a lot of numbers. The point is that it's, quite a small percentage or quite a small volume in the grand scheme of things. Expanding this to a global scale, the above sea level volume of subduction arc magmas is just 1.8 to 4 cubic kilometers per year. That's for the entire globe. What about the underwater arc volcanism? Think island arcs where the volcanoes are still below the waves. Well, for our numbers, these eruptions get fuzzier. We still only get additional 0.5 to 1 cubic kilometer though. even though the air bars are slightly large. Using a maximum volume here of 5 cubic kilometers, that's a fair bit of magma, representing 5 Mount St. Helens eruptions in 1980. What about the gas? Going back to the high end of the estimates above, of 20 grams per kilogram, and let's just keep it as grams per unit volume, as it's much easier to estimate, we get 53,000 grams per meter cubed. Unit conversions arrives at 53 million metric tons of carbon dioxide per cubic kilometer of erupted material. So we have 265 million metric tons of carbon dioxide for arc volcanoes, using our high-end estimates for volatiles. That last part is important. So far, the numbers being used here are near the maximum for volume and CO2 concentration. Using minimum numbers drops that value by a factor of 10. Now, ocean island basalts. Best estimates based on the data is 2 cubic kilometers. Going back to our carbon dioxide flux, and again choosing the maximum 15 grams per kilogram of magma, and again using the same unit conversions, arrives with 81 million metric tons of carbon dioxide. Finally, mid-ocean ridges, where plates are pulling apart. This gets a bit problematic. First and foremost, most of these eruptions occur deep beneath the ocean. CO2 erupted there doesn't degas to the atmosphere. There are chemical reactions and the like that will bind it earlier, but for this exercise, we're just going to keep it simple. Based on observations and models, and ridges erupt 3 to 4.5 cubic kilometers of magma. They intrude or stuff magma beneath the crust at a rate of 18 to 21 cubic kilometers a year. Adding it together and taking the maximum and ignoring the fact that essentially zero would directly interact with the atmosphere, we get 26 cubic kilometers of magma being erupted or emplaced. Again, going back to the concentration for the mid-ocean ridges, we get 1.5 grams per kilogram, and then running the same unit conversions arrives at 105 million metric tons of carbon dioxide. Adding all of these together, 105, 81, and 265 for the mid-ocean ridges, the ocean island basalts, and the arcs across all of the world, we get a grand total of 451.3 million metric tons of carbon dioxide degassed per year. So given, throughout this, I have chosen values near the max every single time. The real number will be smaller. In fact, let's look at those published values that take a longer view, breaking it down more granularly instead of just taking the values near max like I did here, doing a lot more estimates, if you will. The maximum published value is 440 million metric tons. The minimum is 130 million. The value from the paper I introduced at the very beginning, the 2011 seminal paper by USGS scientist Dr. Terry Gerlach, arrived at 260 metric tons as the best value. So my more simple method based on estimates of global magma flux is very close. Not super rigorous. I chose to do something different than just reproduce Dr. Gerlach's to show that the same conclusion can be arrived at using different measurements. This is important. This is how we test science. This isn't just, I am taking somebody else's numbers and reproducing the exact same thing in the paper. Oh no, I took numbers that represent the globe instead of what Dr. Terry Gerlach did, which was a bit more granular and a lot more accurate, given the numbers that he had at the time that he published. I tested the same hypothesis and got basically the same result. So we have the number 451 million metric tons, and we're going to keep going with this number, a true maximum. So step 1 and step 2 are done. We have a value for the volcanoes of the world. Now for the human emissions part, the final part. We don't need to play a game of melt inclusions and eruptive output. The methodology is very different. I will go into some of it here, but It's all published by organizations like the Intergovernmental Panel on Climate Change, IPCC, the International Energy Agency, IEA, and the Global Carbon Project. If you have in-depth questions, send the show an email, or better yet, jump into the source material. You don't have to just take my word for it. That's why we publish things as scientists. That's why if you know enough and willing to take the time, you can go derive it all from the first principles and follow the same rubric that is set out in these publications. So let's start with fossil fuel. The organizations that I just mentioned above estimate fossil fuel numbers from values that are produced independently by legally binding international trade data, customs ledgers, and national energy taxation registers. It's not scientists trying to estimate something through proxies. These numbers are accurate because of the requirements of modern reporting. Scientists just get to use the data. So, using the type of fuel being sold and what it will produce when burned, we can account for nearly 90% of human emissions. There are, of course, non-fossil fuel sources as well for carbon dioxide, and those are a bit harder to pin down. Generally, we're talking about cement. If this is a surprise, it's because you don't know how it's made. We take limestone, calcium, carbon, oxygen 3, that's what limestone is, and heat it to get calcium oxide. What's missing when you get calcium oxide from CaCO3? Carbon dioxide. It also takes a whole lot of heat to get limestone to break down like that. The heat? Yeah, often we almost always use fossil fuels. I don't want to get into the weeds here, but we're looking at about 8% of human emissions. New technology could bring that number way down. Building materials move slow because of regulations. Regulations are very, very important. I live in an earthquake zone. I wish I could speed up the testing and adoption of these technologies, though. The last bucket of human emissions is land use, deforestation, soil degradation. We can model this and make measurements, but the data here is a bit fuzzy. Then again, it is a very small factor than the first two. We're looking around, somewhere in the realm of 2%. Breaking down, fossil fuels emissions clock in around 33.3 billion metric tons, leaving all the rest at 4.7 billion metric tons of carbon dioxide. Remember the volcanoes, our number? 451 million metric tons? Or if we want to make it the same so we can compare it, we're looking at 0.45 billion tons. Or just 1.2% of what we humans produce. So where does that leave us? We've gone from the microscope pressure vessel of an olivine crystal to the massive plate tectonic reality of subduction zones. We've looked at the bubble problem, played the geochemical buddy system, and mapped out all the trend lines of global arcs. After all that math, all the sifting through the gas ratios, the trace elements, we arrive at the bottom line. Yeah, volcanoes emit carbon dioxide. Sure. They are, you could argue, the heartbeat of the planet's natural degassing. They are definitely one knob in the whole climate system that the Earth just does without us. But when you look at the total global budget, the contribution from human industrial activity is just different. It's orders of magnitude larger. The idea that volcanoes are out-emitting humans just doesn't hold up. The data doesn't support it. I I hate to say that it's a myth because there's not much truth to it other than volcanoes do emit carbon dioxide. And I don't really understand the reaching for straws to project a viewpoint that falls apart when we just look at the data. I hope this episode gave you a bit of a window into how we actually know what we know. Science isn't a black box or a magical guess. So often it's a painstaking process of cross-referencing different things like bubbles, isotopes, and ratios to build a clearer picture of reality. It's messy. It's full of error bars. And sometimes it takes a decade just to get one measurement right. But it's how we move from I think to we know. So we know that humans emit way more carbon dioxide than volcanoes. Okay, so this wraps up season 2 of Whimsical Wavelengths, the science podcast. And as I've already mentioned, it's been a wild ride. I hope you've enjoyed peeling back the curtain on how we make science as much as I have for this final episode. To reiterate, I'm taking a break for the rest of summer, planning to be back on September 14th. Encore editions will fill the gap to keep the feed fresh. It's also a time to re-listen to some of my favorites in the back catalog. So hopefully life doesn't throw a wrench into everything I've planned for the start of season 3. And if it does, I'll do my best to communicate about it, should it be delayed. Remember, leave a rating and a review in your podcast app. Tell a friend about it. This is literally the best way to spread whimsical wavelengths and get it into other people's ears. So much is planned for season 3. Well, I'm Dr. Jeffrey Zirk. I'm signing out, and I should be back in your feeds with new episodes starting September 14th.
In a world so chaotic, so misbehaved, echoes of melodies remind us it's all waves. Colors weave stories painting the sky, swaying to rhythms as the galaxies fly by. Ooh, we're tuned in, feeling the beat of the unknown. Can you hear it? It echoes deep in our bones. Through this melodic maze, our minds explore, chasing down wonders, always seeking more. Ah,